This is an RNZ podcast.
They say life is stranger than fiction.
And then the deeper down you go, some people even say there could be something like called nuclear pasta, which is where you get different globs of neutrons together, sort of just become this one big sea of neutrons.
But sometimes what we see in movies or read in books is so incredible that it obviously couldn't be possible. Or could it?
You get this collapse when you get to something called the Chandrasekhar mass, where you can't put two electrons in the same place. That's when you start having the electrons and protons merging to form neutrons.
Welcome to Sci Fi, Sci Fact. I'm Bryan Crump, and this is a podcast where we take science fiction's strangest ideas, weirdest elements, most unfeasible plot drivers, and explore if they could actually happen in real life. Maybe they already have. And in every episode, we bring in a scientist from New Zealand's MacDiarmid Institute to explain the theories behind some of fiction's more fantastic flights of fancy, if any theory exists. In this episode, Associate Professor in Physics at the Faculty of Science at Auckland University, Jan Eldridge, gives us her scientific take on neutronium, a material widely written about in fiction, including Star Wars, Star Trek, not to mention the Marvel comics.
Will it be powerful enough to destroy that thing out there?
Negative, Captain. Its hull is pure neutronium. There is no known way of blasting through it.
Not through it, Spock. From inside it.
Tell me how neutronium manifests itself in fiction first.
So this has been going back quite some way, and it depends. It's used quite a lot in science fiction novels as well as in the TV series. One of the earliest cases of being in TV was in Star Trek, where Captain Kirk came across, I think it was called the Doomsday Machine, which was this giant machine that would go around eating planets. And they couldn't destroy it because it had a neutronium shield, and they didn't know how it was working inside because of this neutronium shield. So it was a nice way of not having to explain anything.
I think I remember that one. It looked like a giant cigar.
Yeah.
It was sort of sucked planets in, and that got rid of them.
Yes,
and
exactly.
It had very dramatic music that went with it, which of course it would. Yeah,
Yes.
I remember that one. That was a cool episode, that one.
Yeah, no, it is, and I think they had to destroy another like Enterprise type ship to actually destroy it in the end. And so it is, and it's just like it's one of these things that you have to have something in your story to tell the story. So you have to make something up, and neutronium is a good one to do that. And it's been used in other times in Star Trek, like when in Star Trek: The Next Generation they came across a Dyson sphere, and so to make this Dyson sphere, which is a big shield around a star, so you get all the energy from a star rather than just having one little planet. That was made from neutronium. Thor with his hammer, whereas I've done some checking and it's never actually called neutronium, but he does say it was forged in a dying star, and so there's only one thing that happens in the centre of a star, and that must be neutronium, or like at least neutron-rich material.
Yeah.
And I'm sure you all remember, or if you've seen it in Avengers Infinity War, to make the new axe Stormbringer, there's a neutron star that he gets material from. And actually, I was thinking on my way over here, like that actually tells you how maybe you could actually have a hammer like Thor's.
Well, this is the thing, though. Now, it's entirely plausible. Actually, I'll come to that question in a moment because I want to talk a bit about neutron stars first. The kind of star that maybe Thor got the raw material for his hammer from. Now, those are stars that are super dense, and so dense that the weight of gravity has squeezed the electrons and protons out of the atoms. Is that a fair estimation of what a neutron star is?
Yeah, pretty much. I mean, so the good news is our sun is not going to become a neutron star. You have to be about 8 times the mass of the sun to get to the point where you've got heavy enough elements in the core to actually form this neutron star. So what you actually have to do in a star to get to a neutron star is you have to make at least an oxygen neon core. So that's something about 1.5 times the mass of the sun. It's just nothing but oxygen and neon. If you get to that point, then nothing can stop that collapsing down towards a neutron star. And you're right, what happens is you get something called electron capture, which is a physical process where the nucleus, which has all the protons and neutrons in it, starts squeezing electrons and protons together and forms neutrons. And the thing is actually held up by the electrons. And so if you actually take away all the electrons, that's why it collapses down. And it bounces down to nuclear densities. And so this is the other thing I can just think about, because it's actually the opposite to what people imagined neutronium would be. When they first suggested it, they were looking at the periodic table and realised they had hydrogen and helium. And so hydrogen is just a single proton. Surely you can have an element that's a single neutron. But if you just have a single neutron in itself, it decays to a proton because it's unstable. So it takes about 10 minutes, I think, roughly of that order, for a neutron to decay to a proton. So it can last for a long time. And if you could collect enough neutrons together, that'd actually be quite boring. It would just be a gas. No container could actually hold them. They would escape from the container or make the elements in the container more neutron rich. So even if you could make them, you would lose them. So that's what they imagined it was. But to find actually, no, you've got to make this entire star for neutrons to be stable is the complete opposite to having something that's a single neutron. No, you've got to have 10 to the 6 neutrons together, which is something like 1,000 billion, maybe another billion neutrons to make this neutron star. And actually, one of my memories from when I was doing an undergraduate physics degree was that one of the revision questions we had for our general paper was estimate by using nuclear physics how big a nucleus has to be of just pure neutrons to be stable. And it came out as about the mass of a neutron star. So you can imagine a neutron star is actually just a very big nucleus, but it's not like the little tiny ones that we have in our atoms and molecules in our bodies. It's the mass of a star to be able to make the neutrons stable and stop them from decaying.
Otherwise, what? They will decay. And
they will decay, yeah.
And become what? Decay into did you say protons?
Protons, yeah.
And then what happens? What if you didn't have the mass of a neutron star to hold those neutrons together and they became a mass of protons, what would happen then?
Well, it would go slowly. So this then goes into the idea of radioactive decay. And so we know that if we look at the heaviest elements like uranium, that undergoes fission. And so you've got this element with 238 protons and neutrons, and actually, rather than just the neutrons decaying, it splits in two and loses some free neutrons that go on to cause further reactions. But then you get two lighter nuclei that aren't so big. So you would imagine that if it wasn't massive enough, your elements would just break apart into smaller bits until they get down to typical element sizes, things like uranium, lead, and all the other heavier elements we know of. And we've actually seen this happen recently. So back in 2017, we saw two neutron stars smash together and throw lots of their material out. So you had pure neutronium, which decayed into heavy elements, and it was glowing because it was undergoing radioactive decay. And that's where a lot of the gold, silver, and platinum end up. So, so we've got stale neutronium in our jewellery.
Now, when two neutron stars collide, wasn't that what created a whole lot of gravitational waves that we were able to detect and then say our gravitational waves do exist? They're not just a theoretical thing. Am I remembering rightly?
Yeah, so that was, I think it was something like the 10th signal we'd actually detected. So the first one was way back in 2015, but it was a black hole, which is uninteresting because there's no stuff there. It's just a black hole. But with neutron stars, there's stuff there. And so what people got really excited about that one was you could see something. It wasn't just detecting those gravitational waves. You could actually see light coming from the material from these stars being shredded apart. And so it's kind of the confirmation that these things are made of neutronium, because that process I just talked about of like where you've got this one big nucleus and it's shredding into lots of little nuclei, we could see that, and you can tell from the spectrum of the light you were seeing that you were seeing those heavy elements being formed and decaying down to lighter elements.
Really? So even with two neutron stars, the protons and electrons, what have they been, when gravity does its work and squeezes them out, what happens to those protons and electrons? Do they become neutrons too, or do they get spat out?
I'm trying to think about how to explain this.
Yeah, I bet it's tricky. Give it a crack, JJ.
Yeah. So, I mean, let me talk about the forces, right? So in the universe, there's 5 forces that we worry about. And there's one that we always sort of mumble over as physicists, because there's gravity that holds you on the floor right now. There's electromagnetism, which holds your atoms together and like stops your hand from going through the table because the charges repel.
There it is, working right now.
Precisely, thank you. And then there's the strong force which holds the protons together in the nucleus. And you need the neutrons as well to try and have extra strong force to make sure your nucleus doesn't fly apart. But then there's this thing called the weak force. And we always mumble over it and go, it's something to do with nuclear decay. And actually it's the weak current or this weak reaction that's going on that it's either the inverse reaction when you're forming your neutron star, that you're squeezing your electrons into your protons. What's really happening is you're exchanging a weak boson that is turning one of the quarks inside the proton into another one to have a neutron. So that's where it all combines together. And then the reverse reaction happens when you have a free neutron, another weak reaction. They're called weak because they go slowly. And that's where you get the reverse happening. So one of your quarks, which are inside the neutrons and protons, becomes a different type of quark, and you get an electron and a neutrino coming out. To try and it's to do with particle physics. Is all about accounting for different types of particles, and it doesn't make a lot of sense sometimes.
No, it doesn't, but it's fascinating. I want you now to try and explain to me. So what are the elements? You said oxygen and neon would be at the core of a star that's going to turn into a neutron star.
Yeah, that or iron. So it's
iron.
Normally it's a completely iron core, but you can get different types of element would do it. It's just you've got to get as far as having nothing but oxygen and neon.
Now, why does it just start to implode and become just a neutron star? Why does that happen at a point in the star's life? Can you explain that?
Yeah. So stars go as far in their burning as they're got enough temperature in their center, because if you're making heavier and heavier elements by smashing them together, you need to go to higher and higher temperatures, which means higher and higher masses, because then you've got more pressure pushing down at the center. And you get this collapse when you get to something called the Chandrasekhar mass, which is the maximum mass something can be supported by electron degeneracy pressure, which is where you can't put two electrons in the same place. And if you get to that mass, then depending on what that core is made of, that's when you start having the electrons and protons merging to form neutrons. And it's just what's effectively happening is the electrons are trying to go faster than the speed of light, but nothing can go faster than the speed of light. And so the thing keeps on collapsing. That's where everything squeezes together. It's wonderfully beautiful maths. But again, it's just this idea that you're trying to link quantum mechanics with special relativity. And that's what gives you this fundamental limit, that you can't make anything bigger than this and be supported by normal matter, which is why it's got to collapse down to a neutron star.
Does a neutron star come out of a supernova?
Yes, exactly. Because when you form these neutron stars and you're putting those electrons and protons together, you emit a lot of another particle called a neutrino. Now, a neutrino is a ghostly particle, and there's 100 billion of them going through your fingernail right now, but you can't feel them.
Thank heavens for that.
Yeah, exactly, because they're coming from the sun and they're being produced in the nuclear reactions going in the core of the sun, which is actually one of the ways we know nuclear fusion is happening in the sun, because we can detect these neutrinos, but only one in a couple of trillion. But in a supernova, you're producing so many of these neutrinos, that's where the energy comes from that explodes the star. So you form this neutron star, you're producing all this extra energy, especially as it's collapsing down from something about the size of the Earth to something about 10 kilometers across, so about the same size as Auckland. And that releases all this energy, all these neutrinos, and that's what explodes the star. So a neutron star is definitely at the core, the heart of a dying star.
How big is a neutron star again?
It's about 10 kilometres across. So I checked this before coming in. So Auckland is about the size of a neutron star, and Wellington is about the size of the same mass black hole.
Okay, and a neutron star is the mass of how many suns?
1.4.
1.4. So it's the area of the sun more it's squeezed into. It's
yeah.
I can't really. It makes me giddy.
It's billions of times denser than anything. So if you had a teaspoonful of it, it would be something like 1,000 billion times denser than water.
Right.
And you would go straight through your teaspoon and through the crust of the Earth, and bad things would happen.
Really. So I couldn't. If I picked up, I would. Wouldn't there be a severe? Wouldn't gravity be doing its bit? Like exactly. if I had my teacup before, full of this neutrino, what would happen to me?
It depends how much you've got there, but it would basically, your cup would break, and it would just sink straight through your cup, straight through the floor underneath you, straight through the crust, and go straight down to the bottom of the Earth's core. But then it probably wouldn't stop. It would probably keep on going, because it would be going at some speed when it got to the centre, so it would go down to the other side, come out the floor, and then scare someone on the opposite side of the planet, and then go back. And so it bounced back and forth because nothing would be able to stop it.
Wouldn't that be the end of the Earth?
It might look like Swiss cheese, but it depends. If it was only a small mass, I don't know.
Iron in its neutron star state without electrons and protons, would it still look like iron, the iron we know around us?
No, but yes.
No.
No, because this is the thing. So iron is a nucleus. So it's got 56 nucleons, 26 protons, and 28 neutrons. So as long as it's got 26 protons, it's iron. Even if you add in a few extra neutrons, it will be a different isotope of iron. But the chemistry, if you put it in your chemistry set, would still be pretty much the same, because you have the same number of electrons which interact with the other atoms. Now, one way of imagining a neutron star or neutronium is it's just a pure sea of neutrons. So it's like one big nucleus. And so if you put your iron inside it, it would get quite dilute. And it wouldn't be it would go into that neutronium and just be that big blob. Now, having said that, one of the problems with neutronium and one of the problems with neutron stars is we don't understand what the material actually is. And so we think that near the surface of neutron stars, there are still normal atoms. They're very tightly squished together, but actually they would be very iron-rich and cobalt and nickel and these other heavy elements. And so you'd have this skin of like normal elements, but very dense together, and so you could recognize them as iron. And then the deeper down you go, the more individual atoms sort of just become this one big sea of neutrons. And some people even say there could be something like called nuclear pasta, which is where you get different globs of neutrons together. And the problem is we don't know. And going back to those gravitational waves, that's when we'll know, because that's when we'll see those neutrons being ripped apart. And the thing that will tell us the answer is not just their mass, but how big they are. And so if they're 12 kilometers in radius, that means they're quite stiff. If they're bigger, say 14 or 10 kilometers, that different radius will enable us to try and work out exactly how thick that iron skin is, and also what the structure of these neutron stars in, which we don't know, which we all want to know because that's interesting.
I'm talking to Jan J. Eldridge from Auckland University about neutronium. Now, you've told us how it exists in stars, neutron stars, or at least... is it officially called neutronium?
No, but people might know what you mean if you say it.
So you're giving it a pass. This is what we're going to call this stuff in stars.
Yeah.
You're not breaking ranks too much with the rest of the scientific world doing that, are you?
As long as you don't tell them, it'll be fine.
Okay, righto. Well, let's carry on. Now, here's the clincher, though. It seems to me physically impossible that Thor could have... If Thor had that hammer and he was welding it on Earth, it would just create mayhem. As soon as he put it down, it's gone. Oh, it's gone through the core. It's gone out the other side. He might come back and catch it as it bounces back, but otherwise it seems like, where's he going to put this hammer?
Yep.
Now, what are some of the plot devices used to actually make this super dense material something which you can actually use in science fiction in a way that doesn't stuff the plot up?
Well, they never cover that. And, I think part of the thing is when you look at Thor, it's presented very much, his skills are very magical. But then you have to remember, there's one of Clarke's laws is that any sufficiently advanced technology is indistinguishable from magic. And actually, Doctor Who pointed out the reverse is also true. Any advanced magic is also indistinguishable from technology. So I'm taking this approach, then there's probably something in there that if that is pure neutronium hammer or axe, to be able to lift it, it has to be some sort of anti-gravity device, which again is something that doesn't really exist, but obviously something that makes it lighter so that it doesn't go through the Earth. And I have to wave my hands and say we don't know how that could happen because it's not really physics, although there is one more force I didn't mention earlier on when I was talking about the four forces in the universe. It's something called the Higgs field, which is what gives things mass. So if somehow in the next century we learn how to turn that off, then you could have something that, even though it's so massive, you would be able to pick it up. Although how it judges whether you're worthy or not to be able to lift up more linear, I don't know. But if you remember a while ago, you asked me about the question about how if you had iron in your neutron star, would you recognize it? I think that's one of the key things. Maybe we're not thinking when we're looking at Molyneux and Stormbreaker, which are the axe and the hammer of Thor, that he's not talking about something from the core of the neutron star, which would just evaporate. Maybe it's the material from the surface of the neutron star, which is normal enough and maybe not quite as heavy as the stuff right at the centre, that maybe that's what they're making. And that's when you put it into the hammer, it even becomes less denser. So it's still quite heavy, but it's not going to go and break the planet if you try and put it on the coffee table.
However, despite all this almost incomprehensible talk about mass and density, things like gold are actually the result of neutron stars colliding. So actually you can have neutron stars which have lost their protons and electrons, and yet they can, when they collide, form the stuff of the atoms can reconfigure to form new heavier elements.
Precisely. Yep. Yes. And we see that happening all over. I mean, it's we had a problem. We didn't know where it came from. We thought it came from the dying stars themselves. But whenever we looked at these supernovae, we never saw enough of that material to be able to explain the amount that's on the Earth. And so now we know how many of these colliding neutron stars there are, or we will do soon. We'll actually be able to work that out because, I mean, estimates vary, but there's something like a Jupiter's mass of gold made every time two neutron stars collide, which is quite a lot.
We'd be rich. We'd be rich if we could just harvest that stuff.
Precisely, yeah.
But it's also good to know that you can get your electrons back.
Yeah. I mean, they don't like being on their own. Yeah. I mean, neutrons do decay, and it's well, I think it's one of the first facts I actually learnt about. And if you're actually trying to work out why the universe has so much helium, it's because there were neutrons around, but they all disappeared, so we don't see them now. But we can work out how many protons and neutrons were formed all the way back at the birth of the universe, and we know it must have been roughly equal by just the amount of helium and protons we see in the universe today.
Ah, the birth of the universe. Thanks for listening to this episode of Sci Fi Sci Fact, hosted by me, Bryan Crump, produced by Andrew Robertson, and of course made possible thanks to the incredible knowledge of those brilliant scientists at the MacDiarmid Institute. You can find more episodes of Sci Fi Sci Fact on the RNZ podcast page. RNZ podcasts are also available on Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or pretty much wherever you might find your podcasts. And make sure to follow us so you don't miss out on any new episodes.